Up till now, we've been looking at some relatively low-level simulators, such as SPICE, low-level in the sense that it's analog, some switch-level simulators, which were relating a transistor to a simple switch, and then some gate-level simulators and some techniques that might be used to speed them up. Here we're going to continue looking at that to some degree by and focusing on timing analysis. So the simulators we looked at typically provided timing based on input patterns. So basically there was a simulation given an input pattern, and this is in effect what's called dynamic timing analysis. So you'd have a circuit simulator, inputs and its outputs, as we saw with the previous examples. A static timing analyzer does not consider function, i.e. not specific inputs. Obviously they're inputs, but they're not specific ones and zeros in any particular line. This section is from a book called VLSI Physical Design, From Graph Partitioning to Time Enclosure. A very good book, recommended. Lots of the chapters are online and certainly well worth looking up. So the objectives of static timing analysis as well as dynamic timing analysis are related to improving performance. And if you recall, the layout has geometric constraints such as design rules, cells that overlap, and routability, and timing constraints as well, which would be setup timing constraints, which are long path constraints, and hold, they're short path constraints. So timing-driven placement minimizes signal delay when assigning locations to circuits. So cells or blocks or whatever you happen to be placing, their location is going to obviously impact the delay. Timing-driven routing is going to minimize signal delays when selecting routing topologies and specific routes. So the topologies of the routes can change, and other issues such as what level you're routing on, the number of vias, etc., can all affect signal delays. Physical synthesis improves the timing by changing the net list. So for example, we might change the transistor sizes, so we increase the width to length ratio of transistors to decrease the delay or increase the drive strength of that gate. If it were a FinFET, it would be perhaps increasing the number of fins. You can also insert buffers into nets to decrease propagation delays, or you could restructure the circuit along critical path, and we'll look at some examples of how that could be accomplished. So the primary goal of satisfying timing constraints includes a setup. These are the long path constraints, where we basically specify the amount of time data input signal should be stable before the edge of the storage element. So for example, it might be a flip-flop or a latch, in which case we want our cycle time, our period, let's say, of our clock, to be greater than the combination logic delay and the setup time, and perhaps some variation in the clock arrival times, which we call the skew. The hold time is a short path constraint, so we specify the amount of time that the data input signal should be stable after the clock edge at the storage element. So what we're looking at here is a combination logic delay which is greater than the hold time plus the clock skew. It's easy to visualize these if we look at some of the corner cases. So we'll look at a setup violation. So you let the combination logic delay be infinite or large. And this is a scenario we're looking at perhaps as a finite state machine with some combination logic and some flip-flop storage elements, and it's clocked. And what happens here then, if our combination logic delay is too long, clearly we won't have a cycle time that's long enough to catch what will happen as the data went through the combination logic and was held for a reasonable amount of time as well. So even ignoring the clock skew, which is reasonable for a local finite state machine like this one, it is clear that the cycle time has to be greater than the logic delay as well as the setup time. So that's relatively self-evident, then why it would be a setup violation. Visualizing a hold violation, here we have a corner case again. We let the combination logic delay be equal to 0, in which case sort of illustrated here by this picture here, and that would be representative of the hold time constraint. So in this case the path is too short, and even ignoring the clock skew, which would be reasonable again for that finite state machine, it is clear that the combination logic delay has to be greater than the hold time. Otherwise the next state could be captured as a current state. So it would be a hold violation. With respect to timing, most integrated circuits contain synchronous finite state machines, and this is just an example of what it looks like when it's rolled out in time, so or unrolled if you like. So typically it was our combination logic block and our storage element and our clock, and this is rolled out over time. So it's this register is this register, which is that register, and the combinational block similar. So the maximum clock frequency will depend on things we've seen before, like the gate delays. So that's the logic gates of the combinational logic. So there's delay associated with them, as we saw. The wire delay, so that's charging and discharging load capacitance, and possibly the propagation of signals that we also briefly looked at. The clock skew is the maximum difference in the clock signal arrival between clock sinks. So time enclosure is the process of satisfying timing constraints through layout optimization, so some change in the layout through our place and route, as well as perhaps through netlist modifications. So dynamic timing analysis is not feasible, as it may not be practical and probably won't be to enumerate all possible input and state combinations. As such, designs are signed off, completed if you like, on static timing analysis. So this pessimistically assumes that all paths can be sensitized, that is, they could be excited. Static timing analysis is an efficient linear time verification process that can identify critical paths. And this is important here because this is where the savings really come in. The algorithms for static timing analysis are very efficient. So with static timing analysis, a combinational logic block like the one that's shown below is going to be represented as a directed acyclic graph, and what that means, it's a graph and the edges are directed. So this would have inputs A, B, and C, and the time of transition in picoseconds from the clock are illustrated here. So 0 for A, 0 for B, and 0.6 picoseconds for C. And then the wire, which are the edges, and the gates, which are the nodes, and have the delays in parentheses. And again, these would be in picoseconds. So for example, this gate here would have a 2 picosecond delay. This wire here would have a 0.2 picosecond delay. So this is the corresponding gate per node directed acyclic graph, as well as inputs being represented as a node, and then basically a per sync at the input. So we superimpose an actual arrival time, so that's that AAT of V for every node. And it's clear when you look at this picture that we really don't care what the gates are. We're just really interested in a static timing analysis. So this represents the gate delay in there, this represents the wire delay. So the latest transition arrival time at node V, which V is an element of the set of nodes V, is the AAT. So that's the actual arrival time, and it's the latest. By convention, it's the time of the output side of the node from the beginning of the clock cycle. So as I said before, it's pessimistic in that not every path may be sensitizable. That is, it may not be excitable or used, and it represents sort of a worst case scenario. By the way, finding the longest path in a directed acyclic graph is a problem of polynomial complexity, which makes, for efficient algorithms, but the longest path in a graph in general is a very hard problem. So here I borrowed from that set of notes that I mentioned earlier. Here the arrival times, actual arrival times, are calculated by this recursive function here. And the only thing to point out here is that this part that you can't probably see is where these u's, which we do this calculation over, are elements of the fan-in nodes of node V. And TUV would be the delay from U to V. So the ATTs of the inputs are given, and from that we can then work forward through the graph and find out what all the ATTs at each node are. So it started out at 0, this is 0, this is 0, this is 0.6. And now we have another one here which was 0. We added a delay here of this wire delay of 0.1 and the 0.1 and the 1 picosecond delay rather of the gate itself. So the actual arrival time at the output of this gate is 1.1. And you work through the entire circuit and you calculate the values along the way. Thing to point out is that these operations, as I said, are polynomial time. They're basically on the order of V plus E, but the graph is sparse, so that also has some desirable characteristics associated with it. We can then calculate a worst case critical path through this graph, which is illustrated here. Here was an example where we had to worry about this calculation over a set of nodes, and we worry about what the fan-in is. This was another that had a fan-in, and this was another. The required arrival time is called the RAT, and it's denoted the RAT of V. It's the latest time of transition that can occur at node V in order for the circuit to operate correctly within a given clock cycle. So unlike the AATs, which are computed upstream, the RATs are computed downstream. And here's an example of it. So we compute the RATs at each node. In this particular case, it's going to be for a given node V, we're going to look at the minimum value of the RAT of U minus the delay of the wire minus the delay of U itself. So the only thing that's to point out here is that the set of nodes that we consider are part of the fan-out nodes of V. And TUV is the delay between U and V, and the RATs of the outputs are given. So in effect, we end up working backward through the graph. There's our graph again, represented with delays on nodes and edges. And we assume that we had a RAT of 5.5. We work back through the graph, and we'd see at this point here it's 5.3. Back to here, we're going to get a 5.3 less 2, so that's 3.3 less 0.25 is 3.05, working backwards similarly on all the other wires. The only other case we'd have to worry about is where we have a fan out. So we'll look at that in a second, but we end up getting back through the graph and we see that we have these values of the RAT. And there's an example where the fan out had to be accounted for. So the slack is basically a term that we're going to use to try to determine where we have to pay some attention in fixing up the circuit. And this is where the correct operation of the chip with respect to the setup constraints, i.e. the maximum path delay, will require that the actual arrival time at each node does not exceed the required arrival time. So it's spelled out in a bit more detail here. That is for all nodes V, element of the set of nodes V. We want the AAT to be less than or equal to the RAT. So we want this constraint to hold. And what that means is that the actual arrival times must be less than the required arrival times. And that's kind of what we'd expect to get out of that. We'd want the actual arrival times to be less than that of the required time. At this point in time, take a brief break.